Hello, hi everyone, welcome back. So this is your Ramandeep Singh. I'm back with yet another lead code problem, that is validate binary search tree. So in this problem we are given the root of a binary tree. So we know what is a binary tree. A tree where for each node I have at most two child nodes. We have to determine if it is a valid binary search tree or not. So a valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's keys, while the right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. So if for a given binary tree these three conditions are satisfied, then that tree is a binary search tree. So let's see how we can solve this problem, how we can validate our binary tree to be a binary search tree, right? So let's see that. So let's first understand it with an example. So we can see that in this example number 1, we are given a simple tree. We are given a tree where the root node contains 2, the left node contains 1, and the right node contains 3. We can see that the left node for the given root node has the key value less, while the right child has the key value greater than the node's key. The first two conditions are satisfied. And the third condition, that is both left and right subtrees, they are also binary search trees. This is also satisfied because the left subtree contains only one node and the right subtree also contains only one node. So all of the three conditions are satisfied and hence this tree is a binary search tree, right? So let's take one more example to understand it better. So let's see this example. We can see that this is the root node right here. It contains 5. Let's check for the left child, which is 1. It contains 1. The key here is 1, which is less than the node value here. 1 is less than 5. So we validate the left child. Now we can see that the left subtree is also a binary search tree. Why? Because it just contains one node. Let's move to the right child. It contains 7. 7 is greater than 5. That's great. Let's check for the right subtree whether this is a binary search tree or not. So let's check for the left child for this node containing 7. The left child contains 6, which is less than 7, while the right child contains 8, which is greater than 7, means this is also a binary search tree. Let's move further. This left subtree must also be a BST, which it is. And the right subtree must also be a BST, which it is, because they contain only single node, right? Now, what we want is, we want to write a code to solve this problem. Let's see how we can do that. Now, to solve such kind of problems, what we have to do is, let's just see. Okay, so let's think about it. Since we need to validate a binary tree, so let's say we have this node, we want to validate this node. What does the validating a node means? Means this particular node must exist within a certain range of values which we define, right? Let's say 6. We know that 6 must be less than 7, but it must be greater than 5, right? That's what we want. So there is a certain restriction for the values of 6, right? There are also certain restrictions for the values of 7. What? Let's think about it. We know at this point that the value of 7 must be greater than 5, and we do not have any upper limit at this point until we arrive at this child, right? So at this point all we know that its value must be greater than 5. Let's include this child. Its value must be less than 8. That is the range of this range for node number 7. For 8, its value must be greater than 7, and we do not have any upper bound for it, right? Its value must be greater than 7, and let's call it, let's say, infinity, means a very large value. So that is the range for this node. For this node, we know that it can't go less than 5, right? So it must be at least 6. And on the other side, on the other hand, it cannot go beyond 7. So the value must lie within this range. So we are not including these values, these corner values 5 and 7. We can't include them, right? So they are open braces. And for this node as well, what we want is, we know that its right bound is 5. Its value cannot go greater than 5, while the left side is negative infinity, right? And for 5, what we have is negative infinity, and on the other side it is positive infinity, right? So these are the range of values that we have for every node that we have been given here, right? So how can we solve this problem? So this is the very first observation which we find when we are understanding the problem statement. Let's move to the next observation, right? First we define that there is a certain type of range. So that means once we define that there is a certain range, how we can validate node number 5? If its value lies within this range, then it's good. Let's move to the left node. If its value lies in this range, then it's good. Let's move to the right node. If its value lies in this range, good. Move to left. If values lies here, good. Move to right. Values lies here, good. So that's how we validate every single node of the tree. So validating every single node of the tree requires the traversal of the binary search tree. And that we can do recursively. We can see that we are simply repeating a certain procedure again and again. So we are simply comparing the value of this node with these values, whether this lies within these boundaries or not. And this task has to be repeated for every node, for the left child, for the right child, and then for the entire left subtree, and then for the entire right subtree. So here we can think about recursion. So whenever we think about recursion, we need a recursive function. So let's define a recursive function. So let's say we have a recursive function. So let's call it check. Let's call it check, right? So let's define a recursive function check. It simply checks for the values that we want to check. So let's define a function check. Okay, let's define it over here, CHECK. So this function, what do we need in this function? We need the current node, right? We need the lower bound, let's call it LB. We need the upper bound, let's call it UB, right? Now, what else do I need here? What else do I need? No, I do not need anything for the current node. So let's say this is the root node that we have. It's 5. So let's check for the 5. What we can do? We want to check whether this 5 lies in this range or not. If it doesn't lie, that means we return false. This is not a valid binary tree. So this is a Boolean function. It simply checks whether the tree is valid or not. So the first condition that we can think of, if this node value, let's call it node value, is either less than or equals to ULB, this is the first condition that we can think of. Or if this value, node value, is greater than or equals to UB. means the current node contains the key which is outside of this range which we are passing. In this case, we'll be returning false, right? Return false. That's the very first simple condition that we can think about. Let's move to the next condition, right? Let's move to the next condition. What can be the next condition? This condition has to be validated for every node of the tree. That means call the same check function for the left child. So let's call it node left, node.left. Now we have to define the range for that left node, the range for the key. What can be the range? Since we have a left child, the range is the value of the left child must not exceed this node's value, right? It must be less than this node's value. So its right boundary is simply node dot value. What is the left boundary? We can go as small as LB, right? So we are calling the same function for the left child of the given node. And not only this, we also have to validate for the right child as well. Check and. We use AND operator here. And call the same function check for the right child. So node dot right then what do we need? Call the same function for the right child, and then what is the boundary for this right child? The boundary of values. It is, we know that the value for the right child must be greater than the current node's value. So node value, and also it should not exceed this UB. It should not exceed this UB, right? So these are the two conditions that we need to check. So if both of these check functions are returning me true, that means the left subtree and the right subtree are valid BSTs, and hence the current tree rooted at this node is a valid BST. That's how we check recursively for the left and right subtrees, right? And what is the base condition? Since this is a recursive function, we have to write a base condition. The base condition is simple. All we have to do is, when we arrive at a node which is a null node, right? Which is a null node. When this node is null. In that case, what we're going to return? We're going to return true by default. Return true. Because a null node is always a valid BST, right? So that's how we define, that's how we can define a function in a really, organized manner. So we started from a simple definition of the problem, and we simply understanding the problem statement will simply make your life a lot easier. All we have to do is to just think as per according to the given problem statement, right? And you will arrive at the solution. So let's jump to the code implementation part. So here we have, let's first define that function, that is Boolean function. Let's call it bool check, right? Bool check. And here in this function, let's pass this tree node. Let's call it root, or let's call it node. So we also need a lower bound. We also need a upper bound. Then if this node is null, then we return true. If this node if the value of this node, so here we have to check if the value of this node is greater than equals to ub, or the value of this node, so it's not left, it's val, if the value of this node is less than equals to lb, that means this is not a valid node and we'll return false from here. Otherwise, check, recursively call this function for the left node, and what we're going to pass here is the left boundary for this node is lb while the upper boundary is node's value, and call the same function for the right subtree and also pass the range as well, right? So that's how we'll be calling this function, that's how we'll be defining this function. So here all we need is if this, so we have the root of the binary tree, so if it is a valid binary tree, then we'll simply return check for the given root, right? Let's run this code. Okay, so we need, okay, so we also have to pass the left and right boundary for the root node. So for the root node, it is int min and it is int max, right? Okay, it's ub. Let's submit it. Okay, so let's submit it. So that got accepted. So what I did is, it was simply changing this long, this int min to long min and changing the data types here. So that's all for this video. If you really like the video, then hit the like button and make sure to subscribe to the channel and stay tuned with me. I will see you soon in my next video. Till then, take care. Bye bye.